Okay. All right. This meeting is being recorded and transcribed. All right. So everything we cover, I'll post this in Blackboard as well. Okay. Okay. Let me go back to my PowerPoint. Okay. So, yes, just to continue recap. So alkenes and alkynes from topic 6. And you'll notice in the video that I stop around slide 16. So that's all that needs to be covered in topic 6. And then topic 7, I'm on slide 19 here. That's where I'm starting today. So there's a second video posted in Blackboard that covers the first half of topic 7. Okay. So topic 7 is reactions of alkenes. So that second video walks you through 5 different reactions of alkenes. You have halogenations, hydrogenations, addition of hydrogen halides, and making alcohols, adding water with concentrated sulfuric acid, and the hydroboration reactions. Okay, so those reactions that are shown in that video for the first half of topic 7, you'll have a couple questions like that on your quiz next week, and they'll be presented exactly the way they are in the slides, where it shows you the starting molecule and the reagents that are added. So you guys need to know, you need to be able to recognize when you see those reagents, oh, this is adding an OH, or this is adding a BR, this is adding an HBr, whatever it is. So you have to be able to recognize when you see the reagents, so what's written over top of the arrow, what type of reaction you're doing, okay? And then you have to draw the product. Okay, so there's lots of practice like that in the slides, in the video that I posted, and then I posted more practice in Blackboard as well. Okay, so make sure you guys do that practice to prepare for the quiz. Okay, so we're going to continue today. This is in topic 7. We're starting on slide 19, or maybe 20. It's 19 on my slideshow here, but it's 20 on my other slides that I have printed here. Okay, so the next topic we're going to cover is redox reactions. So a redox reaction is a reaction that involves a transfer of electrons between 2 molecules. So most reactions that you see written out, that you've been writing reactions out and writing their products, and reactants on one side and then the arrow and products on the other side, most of them are redox reactions. So in a redox reaction, one pair of substances is oxidized. And so something that's oxidized means that it loses electrons. And the other pair is reduced, and reduction means that it gains electrons. Okay, so the example that's shown below here, there's a reaction of calcium metal, solid calcium metal with oxygen gas, and the product that's made is calcium oxide. So what we're going to do for the next couple of slides is we're going to look at the charges on these atoms that are in our reaction equation, okay? So we're going to learn some rules about assigning charges, but most of them will be things that you already know from learning about ions and doing the crisscross method for chemical formulas and things like that, okay? Okay, so important thing to remember is that a loss of electrons is called an oxidation. Okay, so any atom that is losing electrons is said to be oxidized. Okay, so this is the acronym to remember. LEO says GER, LEO, L-E-O is loss of electrons is oxidation, and GER is gain of electrons, means a reduction. Okay, so we're going to start by assigning oxidation numbers, also called oxidation states, to each element in our reaction equations. Okay, This is going to help us figure out which elements are losing electrons and being oxidized, and which elements are gaining electrons and being reduced. Okay, so these are some of the rules for assigning oxidation numbers. I'm just going to show you where we're going with this, okay? So the next slide, I have some chemical formulas, and we're just going to assign charges to each of these atoms. So we're going to figure out what's the charge on the oxygen, what's the charge on this iron, what's the charge on this oxygen, what's the charge on this nitrogen, and we'll go through each of these chemical formulas and assign charges to each of these elements, okay? And those charges are called the oxidation states, okay? So how do we know what numbers to put, what oxidation states to assign to different elements? Okay, so number one rule is that elements that are in their elemental form, so are not combined with anything else, have an oxidation state of 0. So plain oxygen gas O2 has an oxidation state of 0. In the example that was on the previous slide, where's my calcium here? So calcium is in its natural state. It's not combined with anything else. So that calcium as a solid has an oxidation state of 0. This oxygen gas as well is in its native state. It has an oxidation state of 0, okay? It's kind of like you ask yourself, what charge does this thing have? Well, calcium metal just sitting in a dish like that isn't charged, or those would all be magnets and they'd be repelling each other if they all had 2+ charges on them. So it's not until they combine with another element where we do this crisscross rule thing to come up with the formula that they actually interact with each other, right? And they form covalent bonds or ionic bonds, so they actually have charges or oxidation states so that they can interact with each other. So any basic element by itself, including the diatomic gases, all have oxidation states of 0. Okay, most other oxidation numbers match what they would be in the periodic table. So the oxidation state of a monoatomic ion is the same as its charge. Okay, so like magnesium is in group 2 of the periodic table, so it has a 2+ charge. Oxygen is in group 6 of the periodic table. It always has a charge of 2- unless it is bound to another oxygen. So when it's O2, it has an oxidation state of 0. Okay, otherwise it's always 2-. Hydrogen has an oxidation state of +1, except for when it's bonded to a metal and it acts as the negative substance is -1, but that's quite rare. And then fluorine and all the halogens. So all these rules really from number 2 until number 5 all match the charges you would already know from the periodic table, okay? So the last rule here is that all the oxidation numbers combined in a molecule should all balance each other out so that the overall charge of the molecule is 0, unless of course it has a charge on it, okay? So let's start with some examples. Hopefully it'll clarify what the heck I'm talking about. Okay, so let's start with Fe2O3. So the first thing, we're always going to start with oxygen because we know its oxidation state is 2-. So I'm going to put 2- in the corner here. That's the oxidation state or oxidation number of the oxygen, okay? Because there are 3 oxygens in this molecule, and each oxygen has an overall oxidation state of 2-, that means that overall there are 6 negative charges because of the oxygen's contribution to this molecule. Okay, so usually how I write this is I write the 2- directly on top of the oxygen, and then I go up like this. So this is an arrow, and I do 3 times 2-, and I write 6- up here. Okay, so that's where that's coming from. I'm multiplying the number of atoms by the oxidation number of the oxygen. So now I can see that the overall charge of this molecule, iron oxide, is neutral. It's zero. There's no charge on it, right? It's a regular molecule. None of these have charges on them except for over here. We have some charges that we'll deal with, okay? So if there are 6 negative charges, that means there must be 6 positive charges also in this molecule to balance out the 6 minuses and make the overall charge of the molecule 0, okay? So overall, that means iron is contributing 6 positive charges. If there are 2 iron atoms, that means that each iron has a 3+ charge. Okay, so that's assigning oxidation states to each element in the formula, okay? You could get there a lot quicker by uncrisscrossing these numbers, right? You'll notice that this 2 on iron, if you uncrisscross it, is 2 minus on oxygen. And the 3 on oxygen, if you uncrisscross it, would be 3+ on iron. And that's correct. But you have to check that not always will there be a 2 here. Oxygen always has to have a formal charge of 2 minus, okay? So this is it. The oxidation state of the iron atom in this molecule is 3+. Okay, let's do the next one. NO, nitrogen monoxide. So my oxygen has a charge of 2 minus, which means my nitrogen has an oxidation state of 2+. And that's it. You guys interrupt me anytime. Are you going to be posting this class? Yes, I'm recording it, so I'll post this later today. Okay, the next one is chlorine gas. Any guesses here? What the oxidation state of Cl2 would be? I have my chat here. Is 0. Very good, Kushal. Yeah. So this is like our oxygen gas. This is oxidation state 0. Okay, so these are not charged. Any element that's like by itself, even if it's a diatomic gas, has an oxidation state of 0. That was rule number 1 on the previous slide. All right, now coming over here to the right, we have a charged atom. Okay, we have ClO4, and that minus is showing that there's an overall negative charge on the ClO4 molecule. Okay, can we go back to the first one, how it went from 6 to 3+? I divided it by 2, Rabia, because there are 2 irons. So the overall charge of the irons has to be 6+. And because there were 2, I did this divided by 2 here. Divided by 2. Because there were 2 of these atoms. Okay? Okay. All right, so over here on the right to our ClO4 minus. So I'm going to write it bigger here so that I have some more space. ClO4, and then the whole thing is minus. I'm going to move that off to the side and put brackets actually. Okay. So I know the oxidation state of my oxygen is 2 minus. So I'm going to put the 2 minus here. And then I'm going to multiply 2 minus by 4. So I know how many total negative charges are because of the oxygen. So we have a total of 8 minus. Okay, and so I just write it up here on top of my 2 minus. So there's an overall 8 minus charge coming from the 4 oxygens that each have a 2 minus charge. Okay. If the overall charge of this molecule is 1 minus, then how many positives will there be over here so that the net is 1 minus? Okay, so the question is, if I put an 8+ here, 8+ and 8 minus, will cancel each other out and the net charge would be 0. But Michaela got it. Excellent. So there's going to be 7 pluses here because, say, in a tug of war between 7 positive charges and 8 negative charges, there is only a difference of 1, okay? And so this is the net charge. 1 minus is 1 more negative charge than positive charges. Okay, so that means my chlorine has a 7 plus charge. There's no number down here, so nothing to divide it by. That's the oxidation state of this chlorine. So the chlorine is 7 plus and the oxygen is 2 minus. Okay, the 8, we just needed to figure that out in order to determine the chlorine, but the 8 minus is not an oxidation state of anybody. It's the number of negative charges totally by the 4 oxygens. Okay. Oh, I see a hand. Whose hand is that? Is there a question?
I'm a little confused. Okay, so we have to ignore. So, in order to look for the charge for this chlorine, we have to multiply the 4 and 2 minus, and then you subtract the minus, so it's going to be 7 plus. But then the charge for the O is still 2 minus.
Yes. The oxidation state of oxygen is 2 minus. Always. Then, in order to figure out the oxidation state of chlorine, I essentially have to do some charge balancing to figure out how many positive charges chlorine must have in order for the overall charge of the molecule to be 1 minus, right?
So
This
what
means 1 minus.
so what if the minus is plus?
If the minus is plus, then this would be 9 plus. I would need an extra positive charge more than the 8 negatives in order for it to be net positive, right? So I'm thinking like I have 8 minus charges and 7 positive charges. So the net of that is 1 minus, right? If I do this subtraction, 8 minus 7 is 1. And who has more negative charges? Or sorry, who has more charges? The negative one does. So if you want it to, if the charge was 1 plus, I would need there to be 1 more positive charge than the number of negative charges.
Okay, got it.
Does that make sense? You're like doing a
Yeah.
tug of war, like balancing, how many things on one side and the other side to make them equal to the net charge.
Okay, got it. Thank you.
Okay, so let's try this CO3
Sorry,
now.
I just had one
Yeah,
question.
yeah.
Um, so when we're writing the formula, it would be Cl7
No,
positive.
you're not writing a formula. The question is to assign oxidation states. I'm giving you a formula and you have to figure out, this is called an oxidation state. It's like, what is the charge of that atom in the molecule? You're just writing this 7 plus and 2 minus. What I have written here in blue, that's what you have to do. You have to figure out those numbers.
Okay.
Yeah. So there's a question like this on your quiz and will be on your final as well. Is just to assign oxidation numbers or oxidation states to each element in an equation. And so you just work through one molecule at a time and you figure out what charges are on each of them. Okay, let's do this CO3 minus, okay? So you guys try, I'll give you a minute. The oxygen is going to be 2 minus. So figure out overall how many negative charges are there in the molecule and then balance them out so that the total overall charge of the molecule is 1 minus. There's a little negative here on it. And determine the oxidation state of the carbon. And when you get it, you can write the carbon oxidation state in the chat. Okay. Yuxian, you got it. It's 5 plus. You're missing a plus. And Michaela, you got it also. You're right. So overall, oxygen has 6 minus. And so in order for this to have one extra negative charge, I only want 5 positives here and nothing to divide that by. There's only one carbon atom. That's supposed to be an arrow. So the charge, the oxidation number on the carbon is 5 plus. Awesome. Very good.
I have
And
a
the last
question.
one. Oh, yeah, go ahead.
Sorry. I'm kind of very confused right now because when we did the iron one, we kind of made it like equal because we had a negative on the 6 and we made the other side a positive 6.
Right.
Is that because we had a number to divide it by?
No, that's because the overall charge of that molecule was negative. I'm going to erase all this stuff. Oops. Where's my eraser? Here. I'm going to erase all this. The way this molecule is written, Fe2O3, it's neutral. It's a neutral molecule. There is no net charge on it. There's no minus in the corner, right? It's not like the whole thing is 2 minus overall. It's a neutral molecule. So if it's a neutral molecule, there has to be the same number of negatives as positives, which is why one side was 6 minus, the other side was 6 plus. So only these two examples, the ClO4 minus and CO3 minus, these are the only two examples on this slide that have charges on them. And so those are the only ones that have an imbalance, where the oxygen is 8 minus and the chlorine is only 7 plus, because we need an imbalance of charges in order for the overall molecule to be negative. Same thing with CO3 minus. There's an imbalance of charges. That minus means that there's one extra negative charge than the positive charges. So had that minus not been there, if this was just CO3 with no charge on it, this would be 2 minus, overall would be 6 minus. The oxidation state of this carbon would be 6 plus. But because the whole molecule has a negative charge, this is now only 5 plus. There's an imbalance between the negative and the positive. Does that make sense?
Yeah, but I'm still kind of confused with how you make it 5 plus.
So you know that oxygen has an oxidation state of 2 minus, and you understand the multiplying by 3, so we figure out how many total charges there are because of the oxygen. You get how we got the 6 minus?
Yeah, I do.
Okay, so the last step is then to use this 6 minus to figure out what goes over here. Okay, so then we need to look at the molecule as a whole. Okay, the molecule has two pieces to it. It has this carbon piece, and then it has this oxygen piece. This oxygen piece total charge is 6 minus. If the overall charge of this whole thing has one more negative than positives, then what does this have to be? The carbon.
So that's 6 minus 1, 5.
Yeah.
But my question is, how do you know it has one negative?
Oh, because there's a minus sign right here in the
Oh,
formula.
okay. I'm so sorry. Thank you.
It's okay. Right? And this one had a minus sign as well. So those are the only two examples where you have an imbalance of charges. The other ones are all neutral.
Also, one question: if
Yeah?
it like a negative sign, negative charge, so the CO3 minus, we still have to put the 6 minus on top of the 2 minus, right?
It's
Or do
the
we just put
6.
the 2 minus?
The 6 minus is not actually part of the answer. It's like a step that we needed to do in our head to figure out the 5 plus, but the 6 minus is not actually an oxidation number of a particular element. It's the total
Okay.
number of negative charges, but that's not what's being asked for. But I write it there anyways. I write it up above. As long as you have the oxidation number, the 5 plus and the 2 minus written on top of each element, then that's how you should write it.
Okay, got it. Thank you.
So this one I should write 5 plus here. Okay, so this is like how your answer should look. And if you have a 6 minus up here, that's okay. As long as you have 2 minus down here. Okay, so for the last one, what charge are we putting on fluorine? So just use like the charge from the periodic table. I'm sorry, I'm going to change my sharing for a second. No, not window, screen. How do I close this? Periodic table. Okay, so fluorine is here in group 7, right? It has a 1 minus charge. So we're going to put a 1 minus charge on the fluorine. Okay, so as part of our rules is that oxygen is 2 minus, and all of these halogens in group 7, these are all 1 minus, and all these in group 1 are 1 plus and 2 plus, and that you should use the charges based on the periodic table. Okay. Okay, so on fluorine, I'm going to put a 1 minus charge. 1 minus. And so what will be the oxidation state of the phosphorus, P? So you have, it's not going to be 1 plus. You have to look, there's 3 fluorines. So there's an overall 3 minus charge from the fluorines. So there's a 3 plus charge on the phosphorus. Okay, so you should put the oxidation state of the atom that you know, and then make sure you multiply it by the number of atoms there are, so that you have the total number of negative charges due to those atoms. And then you can come over to your other atom and figure out its oxidation state. Okay, so this molecule is overall neutral, so the number of negatives and positives have to match, 3 minus and 3 plus. Okay. I just have to mute for a second so that I can cough. I'll be back in a minute. Okay. So we'll do a couple more so that it all sinks in, and then we'll do them as part of reactions, okay? So let's do NO3 minus. So overall, the molecule has a 1 minus charge. So what will be the oxidation state of the nitrogen there? We know the oxygen is going to be 2 minus. Okay, and multiply. And then what will be the charge on the nitrogen? Perfect. Yeah, you're right. Will be 5 plus. Good. So overall, there's a 6 minus charge. And in order to have a net charge of -1, we only want 5 positives. Good. Okay, we'll go down here to the manganese with oxygen here as a manganate. So 2- on the oxygen. Overall, 1- charge. So what's the charge on the manganese? So the total here is going to be 8-, and we only want one net negative charge. So manganese is going to have a 7+ oxidation state. Okay, good. All right, now we'll do the sulfate. So sulfate, what's the oxidation state on the sulfur? We know the oxygen is 2-. Yeah, this one's going to be 6+. So we have overall 8 negative charges, right? 4 times 2- is 8-. And there's a net charge of 2-. So we need 2 more negative charges than positive charges. So that sulfur is going to be 6+. That's good. Okay, for this last one, we have a hydroxide here. So within the hydroxide, oxygen has a 2- charge and hydrogen has a 1+ charge. This is why hydroxides have a 1- net charge to them, okay, because of the oxidation states of oxygen and hydrogen. So rather than assigning them individually to the oxygen and the hydrogen, you can put that the hydroxide, the OH, as a group, has a 1- charge. That means that collectively, these 3 hydroxides are contributing 3 negative charges in total to the molecule, which means the chromium has a 3+ oxidation state. Okay, if you did them individually, it would probably just take longer. You would still get the same correct answer, but it would take longer to be multiplying the 3 here. Multiplying the 3 by 2, you'd get 6- from the oxygens. 3 times the 1+ from the hydrogen would give you 3+ from those. And so in order to balance this out, you need another 3+ over here, right? So that the collection of all of these charges together equals 0. Okay, but this is a long way to do it. Better to keep your hydroxide group together as having a 1- charge. Okay, so let's keep going now and getting into redox reactions. So in a redox reaction, we have a chemical reaction where one substance is going to lose electrons and another substance is going to gain those electrons. So the transfer of electrons is what actually makes the reaction happen. So in order to figure out where the electrons are going, we need to know the oxidation states of every chemical, every element in the equation. So the oxidation states are written in the circled colored circles underneath. So this zinc in its solid form has an oxidation state of 0. The hydrogen is an ion. It already says here that it's H+, so that has a charge of 1+. The zinc is shown to be an aqueous ion that has a charge of 2+. And this hydrogen gas is in its elemental form, so it has an oxidation state of 0. So what you can see is that the zinc went from having an oxidation state of 0 to having an oxidation state of 2+. So did this guy gain electrons or lose electrons? Remember, electrons are negative. So did the zinc gain or lose electrons? Perfect. It lost electrons. So by losing electrons, it ended up with more positive charges. And so because it lost electrons, is that an oxidation or a reduction? That is oxidation, right? So Leo, loss of electrons, is an oxidation. So that means that this zinc was oxidized, and then the other pair, this hydrogen went from 1 plus to 0, so it gained electrons. And so this H plus was reduced. That's an R, reduced. Okay, so this is also going to be on your quiz, identifying which substance is being oxidized and which substance is being reduced. Okay, so it will involve assigning oxidation numbers and then determining which one is gaining and which one is losing electrons. So we'll do lots of examples together, okay? Okay. So here are a
Can
bunch
you
of,
go back to that slide super quickly?
yeah, no problem.
Thank you so much. Okay, that's perfect. Thanks.
Okay. Okay, so here are a bunch of reaction equations that are all redox reactions. So you'll see there's lots of charges. And we have to fill in this table. I did the first two for you to figure out what is being oxidized and what is being reduced. So in the first example, we have zinc here that has an oxidation state of 0 and copper 2 plus, right? So that charge that's there is already the oxidation state of the copper. And when the electrons transfer, we form zinc 2 plus and copper by itself that has an oxidation state of 0. So from that, we can figure out which one is gaining electrons and which one is losing electrons. Okay, so I looked at the zinc is going from zinc 0 to zinc 2 plus, and so this gave off 2 electrons, right? So this is a loss of electrons. And so the zinc is being oxidized, okay? So it's the substance at the beginning, the reactant, that is being oxidized, okay? So for the reduction, the copper 2 plus, so the other reactant, is gaining 2 electrons in order to form copper 0. And so I showed the 2 electrons that are gained there in order to form copper with an oxidation state of 0. Okay. In the second example, there's one new thing. So identifying the oxidation, the copper with no charge on it, right? Copper 0 is oxidized to form copper 2 plus. Okay, so that's written here with the 2 electrons that are lost. And then look what happens to the silver. So silver starts as Ag plus. It has an oxidation state of 1 plus. Because there's a transfer of 2 electrons, I need 2 silvers in order for this to be a balanced chemical equation. So in order for the redox to actually happen properly, we can't have copper giving off 2 electrons and only having 1 silver who requires only 1 electron. Then there'd be a lonely electron floating around with nobody, and it's not a balanced equation. So this 2 is here, and we produce 2 of these silvers because that allows us to use up the 2 electrons that were given off by the copper, okay? So it's not like I'm not going to ask you to balance the chemical equations, but just so you're not surprised to see, oh, there's a 2 here and there's also a 2 there. Why don't we just cancel them out? Those 2's are needed in order for the redox, the exchange of electrons, to actually be balanced. Okay. So let's go through the next one. We're going to have to assign some oxidation states to some of these elements in order to figure out who is being oxidized and who is being reduced. Okay, so let's start with the CO3 2 minus. You guys go ahead and write in the oxidation states of the oxygen and the carbon. And we'll write them for every atom through here. So then we'll do the carbon dioxide next and the water. And we have to identify who is being oxidized and who is being reduced. We can't see it the way it's written. Okay, so once you've finished doing your oxidation states, you should find that the carbon in carbonate, CO3 2 minus, has an oxidation state of 5 plus. The hydrogen here is H plus. The carbon in carbon dioxide has an oxidation state of 4 plus. So you can see that the carbon has changed in carbonate from 5 plus to 4 plus. So it has been reduced. So we'll write it over here, the CO3 2 minus, okay, with the 5 plus carbon here. Actually, we can leave this oxygen out. I'm going to leave this out just to make it simpler here. Okay, so we'll just write the carbon 5 plus. Okay, has gained an electron in order to form carbon 4 plus. Okay, so that's a reduction because it's a gain of an electron, right? It's becoming less positive, which is like becoming more negative. Okay, so you can write for your reduction. It's either going to become less positive or you'll see it as becoming more negative. Okay, so either the positive charge is going to get smaller or the negative charge is going to get bigger for a reduction. Okay, and I think this is supposed to say H2 so that it has a 0. Sorry. I think this is supposed to say H2 so that it has a 0 net charge on it. So the hydrogen would be oxidized from hydrogen 0 to hydrogen plus. but it's not written like that. So we're going to leave this blank. There's no oxidation shown in the equation. Okay, the next one has sodium, neutral solid sodium with an oxidation state of 0, forming Na+. Okay, so that is an oxidation or a reduction. That is an oxidation. So oxidation is basically the opposite of this, right? You're becoming more positive, creating more positive charges by losing electrons, or less negative. So you're just going to show the sodium that has gone from sodium 0 to sodium plus, and how many electrons are lost in that exchange. There's 2 electrons lost because there's 1 being lost per sodium, and there's 2 sodiums that are losing their electrons. Okay, the reduction here is of hydrogen. So H plus is being reduced to H minus. And 2 electrons are gained in order to form hydrogen gas. So that's our reduction. Okay. We're gonna skip this iron one because it's very similar to the ones above it. And we'll continue now with the aluminum one, okay? So there's formulas that are getting bigger and more complicated, right? So the goal here is to look for redox, okay? We want to see which elements are gaining and losing electrons. So once we find them, you don't have to assign oxidation states to everything. So this aluminum that we start with is aluminum 0. And if we go looking for our other aluminum, okay, I have to assign an oxidation state here. So if you know the charge of sulfate is 2 minus, so you can figure out the oxidation state of this aluminum. Okay, take a minute and see if you can figure out the oxidation state of that aluminum atom. Okay, so you should get an oxidation state of 3 plus, which can be achieved by uncrisscrossing these numbers. Okay, so if you recognize that the 2 minus from the sulfate is this 2 down here, then the 3 at the bottom of the sulfate is the 3 plus from aluminum, then you get 3 plus quickly. Otherwise, the sulfate, SO4 minus, so this whole thing as a group has a charge of 2 minus. So there are overall 6 minus, 6 negative charges coming from this whole sulfate as a group. And so because it's a neutral molecule, there are a total of 6 positive charges. And because there are 2 aluminum atoms, those 6 positive charges have to be divided into the 2 pieces, the 2 atoms, so each atom has a charge of 3 plus. Okay, I appreciate 22 plus. No atom is ever going to have an oxidation state of 22 plus. We don't multiply the 6 by 4. But the 4 belongs only to the oxygen. So if you were multiplying by 4, you would be multiplying 2 minus by 4, which would just be finding the oxidation of the oxygen. Then you'd have to figure out the oxidation state of the sulfur, which we're not doing, right? We're trying to minimize the amount of work. So sulfate as a whole is 2 minus, so keep them grouped together. Yeah, oxidation states are like charges, right? Think about your periodic table with your 1 plus, 2 plus. It only goes as high as 7. And then group 8 is noble gases. So really the highest oxidation state you're ever going to get is a 7 plus for the chlorine, those halogens over there. All right, so we have 2 aluminum atoms with a 0 becoming oxidized to form 2 aluminums with a 3 plus charge. And so that is a transfer of a total of 6 electrons, right? 3 electrons are removed for each aluminum atom, and there's 2, there are 2 aluminum atoms. So 2 times 3 is a total of 6 electrons. Okay, can you just guess which is the other element that is going to be reduced? Your options are copper and sulfur and oxygen. That's all we have left. Can you guess, just based on the general trend of what most of our redox reactions, what type of substances they are? They're usually metals, right? Zinc, copper, silver, sodium, iron, mostly metals. Okay, no one wants to answer. It's going to be the copper. So let's figure out the oxidation state of the copper. You can also tell that it's going to be the copper because this is copper 0. So this is copper by itself. This is copper in a molecule. It has to have a charge to be in a molecule. Otherwise, it wouldn't be attracted to anything in that molecule. So figure out the oxidation state of the copper here. So remember the sulfate. I'm trying to put brackets around this. As a whole, has a 2 minus charge. Okay, sulfate is 2 minus. And so what's the oxidation state of the copper in the copper sulfate molecule? Okay, you guys, have you all stepped away from your computers? If sulfate is 2 minus and there's no other numbers, what's the charge of this copper?
2 plus.
Thank you. 2 plus. 2 plus and 2 minus cancel each other out, right? 2 plus on the copper. So we have over here for our reduction 3 copper 2 plus ions. Yes, you ignore the 3 in front. That means 3 of these molecules, right? So if you don't ignore the 3 in front, you have to multiply it by everything. So yes, just figure out the oxidation state like within the molecule. The 3 is there for balancing. Okay, so 3 copper 2 pluses gain these 6 electrons that aluminum gave off in order to make 3 copper zeros. Okay. So the 2 plus going to a 0 is a transfer of 2 electrons, but because we have 3 of these atoms, there's a total of 6 electrons being transferred. Okay. So you don't have to worry too much about the balancing the numbers that are in front, right? The 2 in front of aluminum, the 3 in front of copper. But this is why balance, how and why we balance equations is so that there's no leftover electrons, that everything is transferred from one thing to another. So we have to have 2 aluminum atoms, each giving off 3 electrons in order to have 3 copper atoms that are able to gain those 6 electrons. Okay, and let's do the last one here. So in order to make this, I actually just want to look up your quiz question, but I'm pretty sure let's do this last one by assigning oxidation states to every element in the question, and then we will identify who is being oxidized and who is being reduced. Okay, so you guys go ahead and assign oxidation states to the iron. You can group the nitrate. Okay, nitrate is 1 minus. Keep this nitrate grouped here as well. NO3 is 1 minus. Okay, find the oxidation states of your iron. The Ce, the chlorine, the Fe, the chlorine here, and the Ce here, okay? Okay, so you should get that the iron in the first compound in the iron nitrate has a 2 plus charge. Okay, the nitrate is 1 minus, and there are 2 of them. So overall 2 minus from the nitrates, which means that this iron must have a 2 plus charge. Okay, moving over to the cerium chloride here. So chlorine being a halogen has a 1 minus charge, and there are 4 of them. So that leaves a 4 plus charge on this cerium atom here. Okay, on the other side of the arrow our iron chloride here. So chlorine has a 1- charge. There's only 3 of them. So 3 times 1, there's an overall 3- charge from the chlorines. So this iron must have a 3+ charge on it. And finally, the cerium nitrate. The nitrate has a 1- charge. Multiplied by 3 is 3- overall here, which means this cerium has a 3+ charge on it. Okay, I hope you guys were able to get those. So now we can identify who is being oxidized and who is being reduced. So we have iron going from 2+ to 3+. So that's getting more positive, which is an oxidation. So we'll write here our iron. I'm having a lot of trouble at the bottom here. Okay, so your iron 2+ becoming iron 3+. Oh my God, I can't even write down here. Ah, what's happening? Okay, 2+ to 3+. So that's only 1 electron difference, right? Going from 2+ to 3+. Okay, and then our reduction is the cerium going from 4+ down to 3+. So you can write that in your reduction box over here. And it's gaining 1 electron to go from 4+ to 3+. Okay, so big picture here, you should be able to assign oxidation numbers to each element within a formula. And remember that when you have polyatomic ions, like our nitrates and our sulfates and our hydroxides, that you should group them just to simplify, because those guys are never part of the redox process. If you're an NO3, a nitrate as a reactant, and you're still an NO3, a nitrate as a product, nothing has changed. You're still bunched together with the same atoms. There hasn't been a move of electrons if you're still in the same cluster that you were in before. So those guys are never going to be the ones that are oxidized or reduced. Okay, so assigning oxidation states, keeping the polyatomic ions grouped and bunched together when you're doing your oxidation states, and then identifying that the substance that's becoming more positive or less negative is losing electrons, is being oxidized. And then the substance that's being reduced is the one that is getting a decrease of its positive charge or an increase of its negative charge. Okay, so I just want to show you one more thing and then we'll take a little break. Okay, and then we're going to do oxidation states of organic molecules. I think it's going to be simpler than this. There will be less numbers involved. Okay, so what these molecules are called are the species that's oxidized and the species that is reduced. So we've already figured out how to determine who is being oxidized and who is being reduced. And then there's this other set of terms called the oxidizing agent and the reducing agent. Okay. So the oxidizing agent, okay, sorry, let's go through this example here. So I think we've seen this one already. So in this example, zinc has charge of 0, oxidation state of 0, and on the product side has an oxidation state of 2+. So we already know that this is an oxidation of zinc. And so we say that this substance right here, the zinc solid, is the substance that's being oxidized. Okay? So if you had a question, like here's a reaction equation, circle the substance that is being oxidized, or identify each species that is oxidized and reduced, something like that, okay? So you can label this as oxidized. The other pair that we have is the H plus turning into hydrogen gas, which has a 0 oxidation state. So this H plus is what's being reduced. Okay, so I have reduced down here. So the things being oxidized and reduced are always on the reactant side. Okay, these are just products. So they're not oxidized and reduced. They're what we get out at the end. So the thing that's oxidized and the thing that's reduced are the starting materials, okay? So now some more terminology. If zinc is being oxidized, then the 2H plus that are being reduced, we say that those guys are causing the zinc to become oxidized. So this is referred to as an oxidizing agent. It's the guy that is causing the other thing to become oxidized. So it's like your Uber driver. How did I get here? I used this service, right? How did I become oxidized? I needed this oxidizing agent to provide the materials for an oxidation. And so the oxidizing agent is always the same as the substance that's being reduced. And so likewise, the thing that is oxidized is also going to be referred to as the reducing agent. This guy is what's causing the hydrogens to be reduced, okay? So the thing that's oxidized is also called the reducing agent, and the thing that's reduced is also called the oxidizing agent. Okay, you have to think of it as the one who's causing something else to be oxidized is an oxidizing agent, and it is the same as the species that is being reduced. Okay, the species that causes something else to be reduced is called a reducing agent, and it is the same as the species who is being oxidized. Okay, how fun is that? All right, we can take a break for 5 minutes. And when we come back, we're just going to finish. We have like 4 more slides in this set of notes. And then I'll try and do a little bit at the beginning of alcohols, okay? Maybe like half an hour more. Okay, so let's break for 5 minutes or so. Okay, hi guys, are you back? I'm here. Okay. Okay, so I'm just gonna continue. I think we'll just finish this set of notes for today, and I'll save alcohols for next week after the quiz. It's not on your quiz, so um, no point in doing like 5 slides today. I'm slowly dying here too, so I need to stop soon. Okay, so why redox is important in organic chemistry is that you can use oxidation and reduction reactions to convert molecules from one functional group to another. So in our lesson 7 that I posted on Saturday, topic 7, part 1, you learned some different reactions of alkenes. So you saw that it was possible to take a molecule that has a double bond, say something like this. Oh, what's happening? Sorry. Right, we can take a molecule like this that has a double bond, and we can add, say like bromine, for example. We'll do a bromination. So add Br2, and that's going to break the double bond and put a bromine on each of the carbons where the double bond has been broken, right? By breaking the double bond, you free up an electron and you allow for the bromine to make a connection there instead, okay? So this is a lot of what organic chemistry is all about, is figuring out different reactions you can do to make different types of molecules. So if you have an alcohol, for example, that's shown here, that has an OH on it, you can do an oxidation. That's what this red O in brackets means, an oxidation. And you can change that alcohol into an aldehyde. And if you further oxidize that aldehyde and do another oxidation reaction, you can add another oxygen in and make a carboxylic acid. So you can transform an alcohol into an aldehyde or into an acid just by doing some oxidation reactions. And so that's what organic chemists do. And like, say, pharmaceutical chemists that are making different drugs and molecules that target things, and developing vaccines and medicines and things to try and target specific cells or things in your body that you're trying to treat, is how do we make a molecule that's like specific for the exact target that you want it to find in the body. And so maybe it needs an aldehyde group, and it needs 2 bromines, and it needs an acid group. And so you have to do all these chemical reactions to try and generate the molecule that you're designing for your medicine or whatever it is. So this is part of organic chemistry that's fascinating. So you guys would know about these 5 reactions already of alkenes, so how to break double bonds and add new things to them. Okay, so there's 5 of those in my video from that I posted Saturday morning. That's the beginning of the lesson 7 notes, these notes. And so what is my point? What am I getting to? No, I'm just going on and on about how organic chemistry is cool. Okay, so oxidations are relevant to organic in that you can make aldehydes and carboxylic acids out of alcohols. Okay, so this 1,0 thing that's here means primary. This is called a primary alcohol because the carbon that it's attached to is only attached to one other thing. The other bonds are just hydrogens. Okay, so this is called a primary alcohol. And this is actually at the beginning of the topic 8 notes is on alcohols. So we are sort of getting ahead. That's a primary alcohol. A secondary alcohol is an alcohol that is connected to a carbon, and that carbon is connected to two other things. So these R groups are other carbons, like longer chains, more things that are connected, okay? So there's only one hydrogen here, whereas there were two for a primary alcohol. And when we oxidize secondary alcohols, the result is a ketone, a carbonyl group. And then the last one is a tertiary alcohol. A tertiary alcohol, the carbon that it's attached to doesn't have any hydrogens on. It's like really overloaded and it has side groups or the rest of the chain coming off from all its three other bonds. And there is no way to oxidize a tertiary alcohol because there's nowhere to take electrons and make a new bond. So there has to be a hydrogen available in order to make, to do an oxidation of an alcohol group. Okay, so the last thing we're going to do now is assigning oxidation numbers or oxidation states to organic molecules. So organic molecules means molecules with carbon and hydrogen and oxygen and not the metals like sodium and iron and copper and all those other examples we were doing earlier. Okay, so what's important to remember for this is electronegativities of elements, okay? So back in Chem 100, you would have seen this chart, which is the periodic table, but notice in the boxes, instead of atomic numbers and masses and all that stuff, instead, these are numbers that represent electronegativity values. Electronegativity essentially means like how negative an element is. Think of them as like a magnet, and the more electronegative the element is, the stronger the magnet is. So fluorine up in the corner is the most electronegative element. It pulls all the electrons towards it, okay? So if fluorine was in a room with all of these other elements and electrons walked in, they would all gravitate towards fluorine. Fluorine is the winner of the electrons. And then it decreases as you move away from fluorine. So oxygen and sulfur and chlorine are like the next the next electronegative elements. And then these guys over here way on the left, these metals, are not electronegative at all. Okay, so what's important when we do our assigning oxidation numbers in organic molecules, we're basically going to look at every bond and decide who is winning the electrons, who is more electronegative, okay? So what we really need to just remember is carbon is here, nitrogen is more electronegative than carbon, oxygen is more electronegative than each of them. Fluorine and chlorine are more electronegative as well. Hydrogen over here, it's part of a lot of organic molecules, is less electronegative than all of these elements, carbon, nitrogen, oxygen, fluorine, chlorine, okay? Hydrogen is more of a positive than a negative compared to these guys. Okay. So when we assign oxidation numbers to organic molecules, we're examining each bond. So let's start just by looking at this carbon-hydrogen bond, okay, on the left here. And we have to decide in this bond, who is more electronegative, the carbon or the hydrogen? I'm asking you, who's more electronegative in that bond, the carbon or the hydrogen?
Carbon.
The carbon is, yeah. Yes, this is going to be on our test. So we're going to put a little minus here next to the carbon and then a little plus here next to the hydrogen. So it means we've assigned the sort of like the who's winning electronegativity values in the bond, okay? So then we do this bond. Okay, so between carbon and hydrogen, the carbon is more electronegative. So we're going to put a minus here and a plus here for the hydrogen. Oh, will you get the, no, you won't. There won't be you don't need the electronegativity chart really, because there's carbons, there's hydrogens, and there's oxygens. And by the time we do a little bit of practice, you should just know which one is more electronegative. Yeah, you don't need a whole periodic table thing for that. No, there's no formula sheet for this quiz. Okay, so we keep going and we assign these minuses and pluses. I'm going to remove my circles here. Keep assigning these minuses and pluses across each bond, okay? So now this lower bond between carbon and hydrogen, carbon is more electronegative and the hydrogen is more electropositive. So right now, this carbon feels like it has 3 minus charges associated with it, okay? So the last bond we have to do here is the carbon-carbon bond. Because this is the same atom, there is no net electronegativity difference between those two carbons. So we put a 0 for both of those carbons. It's like perfectly balanced between those two carbons. There's no difference in electronegativity. So the oxidation state of that carbon atom is 3 minus. You add up all of the charges that you have drawn in around that atom. Okay, so this is how you assign oxidation states to organic molecules. You look at every single bond that the carbon is involved in, and you assign numbers like 1 plus, 1 minus, based on the electronegativity around the carbon atom. Okay, so let's do this other carbon atom in the same molecule. So for every bond, the carbon is electronegative and the hydrogen is electropositive. So just make sure that for every single bond, you're putting a minus for the carbon and a plus for the hydrogen. So that carbon also has an oxidation state of 3 minus. Okay. So next we do, this is ethene, right? 2 carbons and a double bond. So this carbon-hydrogen bond will have a minus for the carbon and a plus for the hydrogen, a minus for the carbon and a plus for the hydrogen. And what do you think in between these two carbons? We have 2 bonds. Is one more electronegative than the other? Nope, is right. These are going to be completely balanced. So we got a 0 on either side. So the oxidation state of the carbon atom in ethene is 2 minus. There's only 2 minus charges total on it, okay? So you're going to go through and continue to assign the negatives and positives for each bond in the molecule. And then the oxidation number on the carbon is the only one we're looking for. So then you're going to add up all the charges together and report the overall oxidation state of that carbon. So do we add up the 3 minus, saying the total is 6 minus? No, you do it for each carbon atom. So this carbon atom has an oxidation state of 3 minus, and that carbon atom has an oxidation state of 3 minus. Don't total them together. Remember when we did oxidation states of the other molecules, we're writing the oxidation state of each element. We don't want to join like iron and oxygen together. we want to say what the oxidation number is of each individual element. So for organic molecules, it's saying the number of each individual carbon. So this carbon is identical to the other one. We'll also have a 2- charge. Okay, so this one is pretty loaded. Let's do this carbon, right? This guy that's in the center of all of these other things that are connected. Okay, so who's more electronegative, this carbon or this oxygen? Oxygen here wins, so the oxygen gets the minus and this carbon gets the plus. Now this carbon-carbon bond is 0 to 0, right? Because they're both carbons. And so are all of these other carbon-carbon bonds, 0 to 0. So the oxidation state of this carbon atom is 1 plus. Okay, so every carbon-carbon bond is a 0, 0. There's no net charge. And because of this link to oxygen, oxygen's more electronegative, the carbon ended up with that 1 plus. Okay, and what about for each of these carbons in the CH3? What do you think their oxidation states are going to be? Total. Yeah, they will all be 3-. They're actually all the same as these carbons over here, right? A carbon with 3 hydrogens on it that's connected to one other carbon. So what we drew here is the same as each of these guys. So all of those carbons have 3- oxidation states. So this carbon, and this carbon are all 3-. They're exactly like these carbons over here. Okay, great. So let's just finish with these molecules. You can probably expect a question like this on your quiz. Maybe just one molecule. Assign an oxidation state to each element. So you have to do the oxidation state of the chlorine, oxidation state of this carbon, this oxygen, and this carbon, okay? And forget about the hydrogens, it's okay. So there's 1, 2, 3, 4, 5 oxidation states that we need to identify in this first molecule.
Miss, before you go through that, do we
Yeah,
just going back to the other slide, do we just forget the hydrogen?
forget the hydrogen. Well, the oxidation state of a hydrogen is just 1 plus because it's by itself.
Okay,
So
so
I don't
there's
know
not.
what you mean by forgetting it. Like I'm not reporting it. I'm just writing what the oxidation state of the carbons are. All hydrogens have oxidation state of 1 plus. There's no
Okay,
other bond on a hydrogen ever, right? It can only make one bond.
okay, got it.
Yeah, so it will usually always be 1 plus. Only in like rare bonds will the hydrogen be more electronegative than what it's connected to. Is chlorine the same as fluorine? Yes, in terms of negativity, yeah, chlorine is very electronegative on the right-hand side of the periodic table. Definitely more electronegative than carbon. So just remember that this carbon has 2 hydrogens attached to it, right? So don't forget about those when you're assigning the oxidation state there. So the overall, oh, Rachel, I see your question. 1 second. So the overall oxidation state of this carbon, we've got 2 minuses because of these CH bonds, a plus from that chlorine, and a 0 from this carbon-carbon bond. So if you add all that together, the total is 1 minus, right? The plus and the minus cancel each other out. It was 1 minus overall. So we write it exactly as you did, even though there's C3 plus molecules. 3 carbons with 3 plus oxidized molecules. Huh? This is CH3, like C with 1, 2, 3 hydrogens, right? CH3, so this can be like abbreviated and written CH3. So each of those carbons has a charge of 3 minus, because the only thing I've written here is a 0, 0, but there are 3 bonds between this carbon and the 3 hydrogens. So there's 3 minus charges on the carbon, that's why. Does that make sense, Rachel? Okay, good. Melissa, does the double bond count as 2 plus to the carbon? So oxygen, yes, it does. So each bond is like 1 minus. So you can think, yeah, each bond is 1 minus. So there's a minus to a plus here, and then the other bond is a minus to a plus. So overall, this oxygen is 2 minus, which makes sense, right? An oxidation state of oxygen being 2 minus. And then this carbon has another 0, 0 here. So the oxidation state of that carbon is going to be 2 plus. And then this last one, we've now done a couple times, right? This guy is 3 minus. Okay, so is that okay for the first molecule? Does it make sense where all the zeros and minuses and pluses came from? So you could get a molecule like this on your quiz, and this could be like a 5-mark question because you have to write the oxidation state of 1, 2, 3, 4, 5 different atoms and a mark each. So put a little star next to that one, because 5 marks is a lot of marks for one question. Okay, and let's keep going and practicing the others, okay? So you guys go through and assign your minuses, and just be careful anywhere you have carbons that don't forget that they have hydrogens connected to them that aren't shown, okay? Like here, right? That's a CH2, so there are bonds here to hydrogen. Okay, on this middle molecule, there's no hidden bonds. Okay, wait, why did the one with chlorine only have 1 minus? Chlorine is only forming 1 bond here, connecting to that carbon, and chlorine is more electronegative than carbon, so chlorine got this minus that I have here in the corner, and that's it. The carbon got a plus. There's no other connections, bonds, nothing else touching chlorine, so it just has that 1 minus charge. The difference with carbon is that carbon forms 4 bonds. So you can have 4 charges coming from the 4 different places, right? The 4 different bonds that it makes. I did not ignore hydrogens coming off. The hydrogens are coming off of this carbon, they're not connected to the chlorine. Right? The chlorine is over here, so the oxidation state of the chlorine is 1 minus. And then next we do the oxidation state of this carbon. It has 4 connections. Yeah, okay, good. Can we do, yes, we'll do all of them. Okay, I'm gonna start going through these chlorines. So each of these chlorines is going to be 1 minus. Oh, hold on a second. Okay, so this oxidation state of this carbon will be 1, 2, 3 plus. The oxidation state of the oxygen up there will be 2 minus, right? It has 2 minuses. So remember, if there's a double bond, you're doing the electronegativity differences of each bond, okay? So if there's a double bond, I have 2 sets of like the minus and plus here on either side of the double bond, okay? So each of those is for one of these connections. Okay, and then I have a 0, 0 between these 2 carbons. So that's 3 plus for this carbon here that's underneath that double bond. And then the other side of the molecule is totally symmetrical, so it should be the same. Okay, so this carbon will also have a 3 plus oxidation state, and this chlorine will have a 1 minus oxidation state. So will this guy. Okay, so we've got 1 minus here, 2 minus for oxygen, 3 minus for that carbon. Oh, sorry, 3 plus for that carbon, 3 plus for that carbon, 2 minus for this guy, and 1 minus for this chlorine. Okay. Is that okay before I move on to the last one? Okay, so Rabia, you got to look at each bond, okay? So let's start here with this carbon atom, okay? This carbon is connected to another carbon over here, okay? So when we look at a carbon-carbon bond, you know the electronegativity difference is like there's electrons in this bond, right? And they're sharing electrons. So if the electrons are more attached to one atom than the other, that atom is said to be more electronegative. So in the case of a carbon-carbon bond, there's no difference. The electrons aren't like happier closer to one than the other. They're completely even like this. So there's no difference in where the electrons sit. However, if I have a carbon-oxygen bond, oxygen is more electronegative than carbon. So these 2 electrons that are in the bond, I'm trying to draw an electron here, 2 electrons, these guys sit closer to the oxygen atom than they do to the to the carbon. Because oxygen is more electronegative, these electrons are more over here. So what that just means is oxygen is more electronegative than carbon. So when we're assigning these oxidation states, we put a little minus closer to the oxygen and a little plus closer to the carbon. It shows that this bond is like a magnet where the negative end is closer to the oxygen and the positive end of the magnet is closer to the carbon. And then we have to do that for every single connection between the carbon and all the other atoms it's connected to. So if I look at this this dot that I have here, I do have a carbon connection to an oxygen. So I'm going to put a plus here and then a minus next to that oxygen, exactly like I did here. Okay. Then I have to continue and do that for the other connections between this carbon and the other atoms it's connected to. So it's also connected to this carbon, but in a carbon-carbon bond, the electrons aren't more attracted to one than the other. So it's totally neutral. We put zeros, like it's not magnetic at all. So we put zeros like that. Then I have another carbon-carbon bond here. So I put zeros. Okay, because this connection between carbon and carbon, there's no difference in electronegativity. Now, I only have 3 bonds here on this carbon, so there is another one to a hydrogen here. And when I compare the electronegativities, I'm going to go back to this chart. When I compare the electronegativity of a carbon, it says 2.55, to a hydrogen, which is only 2.2, carbon is more electronegative, so more minus, than the hydrogen. Hydrogen is more plus. So in my carbon-hydrogen bond, the carbon gets the minus charge, and the hydrogen gets the plus. So a minus for the carbon and a plus for this hydrogen. So now if I look at my very crowded carbon atom here, I should have 4 charges that are telling me the electronegativity of the carbon atom in each of its 4 bonds. So I have 2 zeros, right? I have 2 green zeros. Those come from carbon-carbon bonds. I have a plus from the connection to oxygen, and I have a minus from the connection to hydrogen. So that carbon has an oxidation state of 0 because the plus and the minus cancel each other out, right? We're adding up all of these charges. So the most carbon can ever be is 4 plus or 4 minus. And it would have to have all 4 pluses around it or all 4 minuses around it. I don't know. Did that help a little bit? Are we crying emoji less? Okay, good. Thank God. Okay. So let's keep going and let's do this carbon next, okay? This one that's at the bottom of the V, okay? There's 4 connections there. So just go through each bond and assign either 0, 0 if it's a carbon-carbon bond, or minus and plus if it's a carbon-oxygen bond, or I didn't draw it on here, if you have a carbon-hydrogen bond, the carbon is more electronegative than the hydrogen. So you just draw like little minuses and pluses in there, and you should have a total of 4 symbols around this carbon that you can add up together.
Okay, can I ask you a question?
Yeah, for sure.
Because I think what's confusing me is how you're separating the carbon like bond. Like if it's a carbon to carbon and it's 0,
Yeah.
why are we not just doing it all at once? Why do you have to separate it?
You're trying to find the oxidation state of an element, like of one carbon. So if in order to find the oxidation state of this carbon, for instance, I need to know how it's being affected by all the atoms that are surrounding it. So if this guy is my focus in the center, right? If this guy is my focus, I'm trying to come up with the oxidation state of this guy. I have to look, okay, here I have one carbon. So that's a 0, 0 electronegativity difference. Then I have to look on top of the carbon. What's this bond up here? And how is it affecting my carbon that I'm interested in? And then what about over here on the left and down here on the bottom? We're focusing on carbon as the central atom and looking at the 4 things that it's connected to. Does that make sense? Okay, so I'm going to keep going writing in these oxidation numbers. So this carbon, because of the 2 hydrogens, should be 2 minus, right? It will have 2 zeros and 2 negatives. So the total is 2 minus. This guy is going to have 1 plus. It has 2 pluses and a minus and a 0. So the total there is 1 plus. This oxygen should still be 2 minus. It has 1 minus from the carbon-oxygen connection and 1 minus from the oxygen-hydrogen connection. And finally, this carbon will be the same as all the other CH3s that we've seen. Oh, sorry, 3 minus, not 3 plus. Okay, how are we doing? So can I get, I don't know, like a thumbs up or something from, let's get some emojis going here. A thumbs up or hearts or clapping from people who are getting it. And you can do a thumbs down or crying face or whatever for anyone who's not getting it. And I'll do my best this evening to get up some more practice. Okay, and I'll post this video as well. So we'll get you guys some redox practice and assigning oxidation states to organic molecules. And then you're all set for quiz 3, okay? So I'll post the topic list for quiz 3. I think there's 4 questions. So there's 4 important things from the alkenes and alkynes lesson. You'll have some nomenclature from the topic 7, part A that I posted, the video I posted. There will be 3 or 4 reactions that you have to draw the products of. I highly recommend flashcards for those organic reactions. Like just put the reagents on one side and then put a drawing of a reactant and a product on the back so that you can quiz yourself both ways. Like if you see the reagent, let me change this. Sorry, one sec. Oh, wait a minute. It's in this slideshow. Hold on. Where are those? These guys. Oh, why didn't you go back? These reactions, right? Oh, stop. Oh God, my voice. Stop. Hold on. Sorry. Play is my thing. Okay, I'm just going to leave it like this. Then it won't play my voice. So these are the 5 reactions that we learned, right? So put like BR2 on one side of your flashcard and then put the drawing, like basically this drawing of the reactant and the arrow of the product on the other side, but leave out the BR2. So when you're looking at the BR2 side of your flashcard, you have to say, oh, an alkene, the double bond is going to break and it's going to get a bromine at each of the carbons. And then when you look at the picture on the other side, you have to be able to figure out um, what the reactant is, like what's written on top of the arrow, right? So from the product, you have to be able to figure out what the reactant was. So those 5 reactions are important for your quiz as well. Okay. Nika, you have your hand up. You have a question?
Yeah, I was just wondering if we could have like a topic list for quiz 3 posted.
Yes, I'm going to post that. Yeah.
Okay, thank you.
Yeah, for sure. Okay. Anyone else have any questions? Okay. Thank you guys so much for joining online. I'm so sorry I couldn't do a in-person class today, but I would not have lasted more than half an hour standing. So thank you. And I will see you next week. And so I'll get this video posted, the recording of this lesson, and the topic list for the quiz next week, and a little bit of extra practice just on the stuff we covered today. Okay, there's lots of practice already in Blackboard of those other video lessons. All right. Okay, have a good evening, you guys. Bye.